Welcome to another Honors Physics video lecture series. Today's topic is rotational kinetic energy. Let's begin with a review of our linear and angular quantities. For kinematics, we had distance, velocity, and acceleration, and their rotational equivalents of theta, omega, and alpha. We began our study of dynamics by looking at mass and inertia, which has its rotational equivalent as moment of inertia. We then moved on to force, which has its angular equivalent as torque. That led us to a discussion of work. Work has a linear format as well as an angular. Work then led us into a discussion of change in kinetic energy with the work energy theorem, and kinetic energy again, expressed as K or Ke, has an equivalent in rotational form as well. Let's begin by taking a look at work. In the linear form, work is defined as the product of the vector force times the displacement. This means that those two things have to be parallel to each other in order for work to be done. In the angular form, work is expressed as torque times the change in angle. Again, a one-to-one substitution from the linear values to the angular values. What that means is, for a system to do work in an angular sense, a torque has to be produced, which requires some distance from the axis and a force supplied perpendicular to it. Those two things, producing a torque, will cause a rotation, which means there will be some change in angle of the rotating system. For kinetic energy, in the linear fashion, that was expressed as 1/2 mv squared. In the rotational frame, that will again go through the one-to-one substitution as 1/2 I omega squared. Let's apply this to a familiar system. Here I have our pulley and our bucket. The bucket, some height above the ground, is said to have potential energy. When the bucket is released, the system will be put in motion, and that potential energy will cause a rotation in the pulley and the bucket to have linear velocity, therefore converting that potential energy into a linear kinetic energy and a rotational. If I begin with my statement of conservation of energy, to begin with I had potential and I end up with kinetic. That kinetic is comprised of a linear aspect and a rotational aspect. Substituting in for their quantities, potential energy is the mass of the bucket times gravity times its height, being that all the energy existed and began in the bucket. At the end, the bucket was moving with some linear speed v and therefore has kinetic energy. But the pulley is also in motion, which will require some of that energy. Substituting in for the moment of inertia of the pulley, and then simplifying my expression, I end up with an expression that looks like this. If we remember the difference between linear and angular, v is equal to r omega. So the linear velocity of the bucket is related to how fast the pulley rotates. If I were to square those quantities, I get v squared equals r squared omega squared. Looking back at my equation, I can isolate that r squared omega squared from the rotational aspect of the pulley, which I see as related to the linear motion of the bucket. Multiplying both sides by 2 and factoring out the v from the right, I get this expression. Dividing by the mass term and taking the square root gives me an expression for the speed of the bucket as it's falling by using conservation of energy.